All right, now we're going to do the fourth problem from the fourth ACSL quiz in 2012-2013. This is a digital electronics problem that wants us to find how many ordered quadruples make the circuit false. So as always, we're first going to write in what each symbol in the circuit means, so then we can begin to translate it into a Boolean algebra expression. As usual, we're going to go one by one and start with the first operation, which is an A OR. And we know it's going into an OR, so I'm going to put a plus sign, but we don't know what it's connected to, so we'll leave some space and go to the next one. The next operation is an A or a B. And we're going to ignore how it's connected, but that's one section, so we put that in parentheses, and that's an A plus B. Then we can continue on to the next grouping, which is going to be the B connected to the C with an AND. Again, this is in parentheses, and we don't care how it's connected to the other terms because we'll deal with that later. The next one is the C and the D connected by a NOR. And remember, our parentheses are very important here. And the not goes above the parentheses C or D, not separated. And then the final operation before we get to the next level of the circuit is the not D. So we'll just put that to the side as well. Now we're going to begin with the second level of the circuit. And we're going to start with the NAND that is connecting the A or B and the B and C. And we can put those two groupings in parentheses now and put a not over them. Next, we're going to the AND that connects the C nor D and the not D. And we'll put those in parentheses. So the third level of the circuit begins with the NAND part connected to the A OR. And we'll put that in parentheses. And then finally, bringing the whole circuit together is a XOR, and that's connecting the grouping of pink parentheses and the grouping of gray parentheses, and that's our last operation. So to rewrite our expression, that is the full Boolean algebra expression that we're going to simplify and find how many ordered quadruples make that circuit false. So as we saw, the digital electronics circuit simplifies to this Boolean algebra expression here. And now we're going to just start by De Morganing those two terms up there so we can begin simplifying our expression so that when we eventually find out which or how many ordered quadruples, we don't look for a lot of unnecessary terms. And that's what you get when you De Morgan, and I'll just rewrite the second part of the equation so we don't forget about it. Now we see that we can De Morgan again. The De Morgan's rule is very important clearly in all of these problems, so make sure you know it very well. And we're going to use that rule again here to simplify the first term, and we can also do it to the second one, and we will get to that afterwards. But yeah, make sure you really know that De Morgan's rule. So now we are going to just factor out a common B naught in the first expression so that we can make our simplifying a little bit easier. And as we can see, the B naught factors out to an A naught plus 1. And A naught, whatever A naught is, or 1 is always going to be 1. So that term can be simplified to 1, and then B naught and 1 is always going to be B naught. So that simplifies to A or B naught or C naught. And now we're going to De Morgan that second term over there. So we get a not C and not D times not D. And now just rewriting, because the C, not C, not D can just be written as not C, not D. And now finally we're going to take the definition of XOR to simplify this expression even further. XOR means that one is true and the other is false. So for the first term in this expression, we're going to say the first part is true and the second is false, or the first is true and the second is false. And this would cover all of the scenarios, and then we can use the De Morgan's rule to simplify this expression even more and get a fully simplified expression. But make sure you also know the definition of all of the operations, not just and or, but also NAND and XOR and the weird ones that you may not originally think of. So this is what you get when you De Morgan, and then we're going to just factor each of these terms and see if we can simplify any more before we go on to the Broner method. Now we get just distributing the A and C, or AD, or not BC, or not BD, or not CC, or not CD, plus the not A, B, C times not C, not D. And now we can find terms that have both that term and the opposite of itself, which is always impossible. So those terms are 0. And then just rewriting that all again, we get an AC or AD, or not BC, or not BD, or not CD. Now we're going to factor out common terms, and this step isn't 100% necessary, but I find it easier to solve after I do this. If this causes you to mess up, then you can skip it and go straight from this to the Broner method. But as you can see, the groupings in green and pink have common terms, so I'm going to factor out a C from the green terms and get a C times A or not B, and a D from the pink terms and get a D times A or not B or not C. And this is my fully simplified expression that I can then go on to solve through the Broner method, but clearly it's a lot simpler than what we started with, so simplifying Boolean algebra expressions is really important before you get going. Alright, now we're looking for how many ordered quadruples make this false. Now remember that every time you have a different term, the number of possibilities increases by a power of 2. So now that we have 4 terms, there's 16 possible answers for each term. So you make sure to do the 8 zeros and 8 ones in the first column. And then our not B is just the opposite of what B is. And then A or not B, I'm just going through the terms that we need. Now the first part before the plus sign is a C and A or not B. And the truth table for that is as follows. And now we're going to move on to our next part. The first term we don't have is not A. Then we also don't have not C. And we already have the not B. And now we need the not A or not B or not C. So whenever not A or not B or not C is true, this whole column is true. Now we need D and that column, so both the D column and the last column we just wrote have to be true in order for this next column to be true. And that looks like this. And now finally, we need to compare the C and A or not B, or the D and not A or not B or not C. So to make it a little bit clearer, remember we're just looking at this column here and this one over here. So the two that are highlighted in green are the only ones that we're looking at. And that looks like this. Be very careful when you're lining up so you don't get anything wrong. Now we're only looking for the ones that make the circuit false, which are highlighted in pink. And then if we count, we get a total of 6 ordered quadruples. Now, because the question didn't ask for which ones they are, this would be your final answer. All you need is the number 6, not which values for A, B, C, and D satisfy this equation.